Okay, there we go. Hello, everyone, and welcome to today's presentation demonstrating our global collaborative space system development with Oakmont Aerospace, KISPE, and NewSpace Systems. I'm Danielle Cleveland, the marketing manager here at Oakmont Aerospace, and I would like to thank you all for taking time to be here today. Before we begin, we have enabled our Ask a Question feature in the side panel of your GoToWebinar window. So we're having a live Q&A at the end. Any questions you have during the demonstrations, please pop them in there and we will get to them at the end. If you do miss anything that happens during the webinar, don't worry. There will be a recorded version available at the conclusion of today's event that will be automatically emailed to you. So look out for that. And all that said, I'm pleased to introduce NewSpace Systems CEO James Barrington Brown, KISP's Managing Director John Paffett, and Oakmont Aerospace's President, Co-founder, and Chief Systems Engineer Stanley O. Kennedy Jr. Stan, please take it away.
Hey, thank you, Danielle. Hey, really excited to be here and happy.
And Stan, you are on mute.
No, I don't think so. How about now? Test, test.
You're good, Stan.
Oh, well, there we go. Hey, really happy to be here and excited to kick this thing off. At Oakmont Aerospace, we're a woman veteran-owned small business located in Denver, Colorado, in the States. We specialize in rapid and responsive modular open system architectures, and our Acorn product is an enabling technology that we're working with our business partners around the world and our strategic partners, NewSpace Systems in South Africa and KISPE in the United Kingdom, for this demonstration. Really excited to be here and glad that you're here for the ride. Would like to turn it over to James, give a little bit of background on NSS, and we'll go from there.
Yeah, hi everybody, very warm welcome from the southern tip of Africa. Let's hope the demonstration goes as well as the video so far. We're presenting across 3 different continents, so exciting times for us. NewSpace Systems, hopefully a lot of you have heard the brand. We're a component and subsystem maker specializing in attitude control sensors and actuators, GPS receivers. So everything to make sure your spacecraft's pointing in the right direction, doing what it should be doing. We've got ESA trained people. We have ISO 7 clean rooms or ISO 9001 process accredited. Our man Louis is later going to talk about the product that we're going to be demonstrating, which is one of our reaction wheels. But let's not slow things down. I'll hand you over to John Paffett at KISPE.
Thanks, James. So I'm John Paffett. I'm the Managing Director of KISPE. We're a program system engineering company working with clients and partners, really helping to sort of turn their ideas into reality. So as Stan says, we're based in the UK, so actually in the south of England, but we get to work with people all around the world. So we're a team of there's about 30 of us. We're a team of about 20 people with over 30 years worth of experience in the small satellite industry. I guess collectively we've worked on now more than sort of 50 different satellite programs. So we've got a lot of experience in the design, manufacture, launch, operations of small satellite systems. We tend to work with people across a full life cycle of space programs. So from the initial concept definition activities through system design, manufacture, integration, test, launch, and operations. What's nice about our job is we get to work with some really brilliant people and on some really neat projects. Great example, we're supporting Virgin Orbit and Spaceport Cornwall on bringing Launcher 1 to the UK. We're teamed up with Moog on the design and manufacture of their orbital maneuvering vehicle. And we're working with Stan and the team and James and the team on things like the Acorn activity, which is excellent. So some great teams and some great projects to be part of. We're also in the process of developing a fully open source next generation microsatellite platform. So that's really exciting as well. What drives our company really is this desire to stimulate the use and application of space and really to make space more accessible. So we're constantly looking for ways to improve the performance of space programs and reduce the mission costs. And that's one of the reasons why we're really excited to be working with Stan and the Oakmont team on the work that they're doing with the Acorn and with James and his team at NewSpace Systems because that's really helping sort of drive the price performance point. So getting the performance up and driving the cost point down, which is great. What the Acorn does for us is it enables us to take an initial design concept and to rapidly generate what we would call a digital design reference mission, or a DRM. So we can take that, we can iterate our design concept very quickly, we can swap out components and subsystems as we need until we arrive at that desired solution. So that's great. We can then transition that to hardware in the loop testing and ultimately use the Acorn to provide a spacecraft environment for the satellite integration and test. So today's demonstration, which you'll see in a minute, gives us a good insight into some of the capabilities. What I love about the solution is we can take that design and get that up and running quickly, and we can even do hardware in the loop testing without that equipment needing to be sent across to us and physically here in the building. Something that's really useful in today's climate. So the nice thing about it is we get to test out James's kit without him actually having to send it across to the UK, which is useful. So for the purpose of today's demo, we've got the NewSpace wheel. That's something we can physically see and interact with in that simulation environment, which is great. A lot more exciting than watching one of James's GPS receivers or his sun sensor or magnetometer. Wouldn't quite have the same visual effect. So anyway, so I hope you enjoy it. Hope you enjoy today's demonstration. So that's it from me. With that, I'm going to hand you over to Dave Lucky. He's the Acorn project manager at Oakmont Aerospace. So over to you, Dave.
Thank you, John. I appreciate that introduction. Yes, as John was talking about, there's a lot of excitement about this project and what we've been able to do here. So hopefully we can instill some excitement into your day-to-day lives with this experience, and hopefully you'll feel that the new future for spacecraft development is really in good hands. So again, my name is Dave Lucky. I'm the Acorn product manager here at Oakmont Aerospace Incorporated. I've been in this business of space development for about 20 years. I've seen a lot of spacecraft from small down to dishwasher sized, all the way up to more of a bus size. And I've even had the opportunity to work on some interplanetary missions. So with that, I've been exposed to a few different problems that you see in the whole world of developing spacecraft. And most of the time, the sooner you find those problems, the better off you are. As John mentioned, we start with a DRM before you even can do anything with hardware or software. You kind of have to know what you're going to do. So that's one of the first things you have to work on. It helps you derive all your requirements and everything that you need, so you'll be able to build the spacecraft and do the mission that you've been tasked with doing. Part of that is also hardware interface testing. That is always a challenge. Most of the time, hardware shows up and it's in good shape. Everything works great, but then on occasion, there's some issues with the interfaces or other types of performance things that can cause delays and impact your schedule and costs. So those are things that, as a developer of spacecraft, we like to try to avoid those things. We like to be, as John mentioned, and James, involved with our partners locally instead of just being here far away. So we are able to talk to them and work with them frequently. Today's demo, as John mentioned, is going to be about how you might take a spacecraft mission and work it through all the way to ops. Of course, we only have 20 minutes for that, so this is not going to capture everything. But I did want to talk about the team just a little bit. As on the screen here, you'll see Ben Hudson. He's the systems engineer from KISPE. He was basically responsible for all those design reference missions things that John was referring to. Louis, he's a controls engineer from NewSpace Systems in South Africa. And he's been doing a lot of hardware work for us and making sure that our algorithms are working with his wheel. So that's been very challenging. It's definitely been fun to work with them. For my part, I've been more of the facilitator for how do we use Acorn and how do we get that piece of software working so we can do these fabulous things, because it is hard to do those things. And without some type of platform that is compatible with this type of need to work remotely and far away, it's difficult to do that sort of stuff. So that brings me to Acorn. Just to tell you a little bit about Acorn. Acorn is an acronym, of course. It stands for Advanced Configurable Open System Research Network. So that's the name that we use to get with Acorn. We like the name. It's kind of fun. Let's see. So as far as Acorn's internals go, it's we use a lot of common protocols, both internal and external. This is intended to allow a lot of easy integration with different components, whether it be hardware or other software components like ground control systems. As I mentioned earlier, we can do from design all the way up to end-to-end testing and even into ops where you're doing training and you're running emissions ahead of time, mission plans before you actually load them onto the vehicle. So that's a really key thing for us to be able to do. And I just want to show you just quickly here that we are geographically far away. So this is a pretty interesting thing for us to be able to do from these different countries and at this time. And we've been working together quite a bit. So we, I think, probably worn out those internet connections between here and there with all the data that's been flowing. So I just want to mention just briefly the different types of Acorns that we have. The Acorn S is what we have at KISPE with Ben. That one is just basically an executable on a PC that we've included in a shockproof case. It's got a high-end PC to make sure that it can handle all the needs that will be done with when we're developing these missions. Acorn R is a high fidelity VRM type setup, but it's really intended for hardware in the loop. And that's what we have with NSS. They're using the hardware in the loop portion of this, so that's been really a good thing to have for them as well. We also offer an Acorn MT, which is basically a full flat sat. So that's probably one of the more important aspects of when you're finally on to building an actual spacecraft. With an MT, you're able to test out cable signal strengths and weaknesses, interference, cable runs, voltage impacts, and things of that nature that really you can only find if you actually connect things up. Also, we've got Acorn VMs. As everybody in the world is going virtual, we have also got a virtual machine that we use. The virtual machines are really good for helping with constellation design and scaling the missions to larger event-driven things that you'll want to see. So we also offer up some different things that you can put inside of an Acorn. We have basic flight software that we include with it, so you are able to go off and start doing these DRMs without having to have a large effort to develop and to get to that point. So it does offer you that opportunity with that. Also, we have a database included of various different components that are either in use or planned for use that we have specifications for. So then you can just easily switch between those with our configuration GUI, and you can rerun if you want to change your wheel size or something like that while you're trying to figure out what you want for your performance based on the hardware. So with that, you're able to also add your own models and components. So you're not limited to just what we have. You certainly have the ability to add components as well. We do the environments as well. So we've got gravity models, environment variable models, and then we have also the magnet models as well. So we offer a basic and a more complex version of that. We also have a monitor that you can use to do your ground command and control and receive telemetry and see what's happening with the vehicle while you're running it and until you get your own developed. It's also easy to operate remotely, as we'll demonstrate today. We'll be all remote here, well, from each other. We'll have a unit ourselves, but we're able to talk to each other's units far away. It's also a really great testing platform. It's really a place where you can do a lot of things and not have to worry about damaging any hardware, or if you make a mistake there, it's just software, you just start over again. It's very global in this case. As I mentioned, we're using no proprietary interfaces here at all. We're just using regular internet connectivity between the three companies, and there's nothing really special about it. Everything that we're using is an open source or open system type concept. So we'll share that with you as we go. With that, I think I'd like to hand it over to Ben to start with the a little more detail about what the mission is doing.
Thanks, Dave. So as Dave said, I'm Ben Hudson, systems engineer at KISPE, and I've been working the KISPE side of this demonstration. So the mission scenario that has been modeled in Oakman's Acorn for the demonstration today is a design reference mission created by KISPE. So as the Acorn is a space mission design environment, this allows us to do detailed design and testing of satellite missions. So we've used it today to simulate the typical sequence of events of this mission scenario. So the design reference mission itself is an Earth observation constellation consisting of 12 spacecraft. And we arranged these 12 spacecraft in 3 orbital planes, as you can see on your screen at the moment. These are in a Walker-Star configuration as well. So from a mission operations point of view, this would decrease the revisit time to any specific imaging location on the Earth, and also vary the local time of day at which you'd be taking your images. So the spacecraft themselves, as they've been modeled in the Acorn, are based on another KISPE design reference mission, which is known as KIO-1. And this was a design for a small spacecraft which actually utilized the NewSpace Systems reaction wheel that will be demonstrated today, and I'm sure Louis will talk about a bit more later on. So if we talk a little bit now about the Acorn configuration GUI, which is the way in which the user can very easily input a mission scenario into the Acorn. And this allows you to schedule automatic events for the spacecraft to go through, such as times at which to conduct an imaging event and point at the ground, or maybe to go into a sun pointer mode. So this user-friendly configuration GUI also enables rapid testing of a range of spacecraft architectures, as has been mentioned before, as you can easily change out which components are used on board your satellite. So for example, for common spacecraft components, such as sensors, actuators, or power subsystem components, the Acorn has a pre-configured list of real hardware that can be added to your spacecraft design and then tested by simulating the mission. So you can also design your own components in the Acorn, as Dave previously said, and you'd specify a number of key parameters of the equipment that you want to model. So the configuration GUI was used to model this design reference mission in the Acorn, and it will then be simulated today, as we will show you. So I'm now going to pass back over to Louis at NewSpace Systems, who's going to introduce himself and talk a bit about the hardware that we have connected to this demonstration today. Louis?
Thanks, Ben, and greeting from myself and the team here at NewSpace Systems facility here in South Africa. I'm going to tell you a little bit more about the setup that we have here today in the NewSpace clean room. We are going to be using the NewSpace reaction wheel, specifically the T065. And the T065 finds application as a 3-axis torque and momentum exchange actuator for agile and small satellite missions. So today we'll be using one of these wheels in a hardware in the loop simulation configuration as part of the Acorn R. This is very useful because it provides a user with the ability to validate the hardware performance and the simulation models, and effectively creating a virtual flat set. So additionally, it allows us for remote debugging. As you can see on the photo here, we have Dane there on the background, which is currently in that particular photograph. We're assisting us with a certain amount of debugging and connecting of the software. So as we can see in the photo, the T065 wheel is connected via the RS422 port on the left-hand side to the screen. I have here on my left, that's why my shoulder is twitching here to the left-hand side every now and then, just to check that the screens are still showing what we want to see. And then on the right-hand side, you'll see it's powered. We also have a webcam, which is taking a photograph of the reaction wheel. And at the back, it's connected to the 28-volt power supply. So for the benefit of the user, we've placed an optic pattern on top of the wheel, which is then photographed by the webcam in its clamp mounted down. And then for the viewer can then observe the wheel speed changes as we go through the scenario view today, as Ben will be sending the commands from the UK. So I think as Dave will set the video spinning there, we will see that we currently have an anti-clockwise spinning wheel. So any clockwise patterns are just artifacts from the frame rate of the camera and the patterns on the wheel. So as you see, every 15 seconds, the wheel speed is increasing up to 300 RPM, 600 RPM, and 900 RPM until it's then gradually slowed down again. So this is now an anti-clockwise spinning wheel, and the clockwise patterns is just the classic wagon wheel effect that you see. We can do it at higher speeds here in the clean room as well, but for that we need specifically a strobe light, and it's not effective to do that over the internet. So we'll talk about the specific technical issues a little bit later today, but this is just to set the stage and create it for an environment where you can look at the wheel and see how things are happening. So let's pass back to Ben and ask him to tell us a little bit more about the scenario that we'll be simulating this afternoon.
Thanks, Louis. That's great. So this demonstration is going to focus on the simulation of 3 individual spacecraft from that wider constellation, which I described earlier. So each of these spacecraft has been modeled in one of the Acorns we have connected together. So each of Oakmont, KISPE, and NewSpace Systems Acorns has one of these spacecraft modeled inside it. So the demo itself is going to consist of a 20-minute simulation, run in real time, of a typical sequence of events for an Earth observation mission. So the plan today is each spacecraft will conduct a surface point maneuver to emulate the imaging of a target location on the Earth. And for those of you that will notice this fact when we show you the visualization, a push broom technique is not being used for this simulation today, as the imagery data we're collecting is imagined to be in the form of a video. So each spacecraft will then conduct a subsequent surface point at Svalbard ground station to emulate that telemetry and payload data downlink procedure. Also included in this demo, we're going to do a sun point maneuver with the Oakmont spacecraft, I believe. And this is just to demonstrate to you the Acorn's power subsystem modeling capabilities. So I think with that, if we head over to the KISP's Acorn screen, I can show you a little bit about the monitor GUI, which is shown to the user when you're running a simulation. So as you can see on your screen now, this is the Acorn monitor GUI. And what we have here is we have a separate panel open for each of the Acorns connected in this demonstration. So as you can see here with the Oakmont Aerospace Acorn, the KISPE Acorn, and the NewSpace Systems Acorn. And what will happen is when we click start on these and set the simulation running, live data from these machines will be returned to me and displayed on this machine. So this is live telemetry coming from them locations where Dave and Louis are at. So this monitor GUI returns sort of important information to you that you'd like to see during the simulation run. This ranges from attitude and orbit data. So we have attitude rates, wheel speeds, the wheel torques. We also have a few displays showing the power subsystem. So you can see here we have the battery state of charge indicated. And we'll go back to this later on when we do that sum point maneuver, and we can show you how all this changes. So I think now, though, that it's a good time to start during the demo. We'll start the technical portion of the demonstration, and we'll begin the simulation. If Dave has got his live SDK visualization ready.
We're all set.
Brilliant. So we'll click start here and set these Acorns running. So what you should begin to see now is all three Acorns will begin to have their telemetry updated, as you can see there. So this is the live telemetry coming from the Acorn machines. And I think we'll come back to this plenty of times throughout the simulation today. But for now, let's head over to Dave's SDK visualization, and he's going to talk a little bit about how we're going to be viewing this simulation today. Dave?
Thank you, Ben. I appreciate that. Yes, so what you'll see here on screen is a SDK that we're using to display our telemetry as it pertains to the bodies of the vehicles, their attitudes and their orbit locations. So we're actually able to see that live. As Ben mentioned, this data is flowing through from their units to here through SDK Connect. So it's a TCP, IP, UDP type interface. So it's not anything proprietary there at all. We're not using any of the SDK propagators here, and it's not required to have SDK. It is a nice tool to look at stuff and kind of keep an eye on how things are looking through the mission. So we'll be able to do that some today. We'll switch around to some views that we can see what's happening with the vehicle. Again, we do store the data for analysis down the road, so we certainly can have the .a files, .e files, those reviews from the SDK. That's what they ingest to show these types of things. But for us right now, we're just showing you some live data. And with that, I think I'll hand it back over to Ben, and we can talk a little bit more about what these vehicles are going to be doing.
Thanks, Dave. So Dave's got this live SDK view up at the moment. So if we zoom in on the Oakmont spacecraft, we should see it's going to begin to conduct its first surface point maneuver. And what we have here is it's going to come into view of the Port of Busan in South Korea and begin imaging that target. And just a quick note on why we have picked certain imaging targets for the mission scenario today. For the Acorn spacecraft, for example, we've picked the Port of Busan because as we're recording sort of video data here, dynamic targets such as ports and airports are interesting locations to record with lots of moving objects in view. They're also good for calibrating your imagery payload. So after this imaging event is finished, the vehicle will perform a sum point, and that gives a chance to show you how the Acorn can model the power subsystem. But we'll come back to that later on. I think for now, if we change back over to my Acorn screen, and then we'll hand over to Louis, who's going to talk a bit more about the reaction as we have the NewSpace Systems spacecraft will begin to conduct its own surface point very shortly. So Louis.
Thanks, Ben. If we just have a look at our mission time, I see we're here at 8:32:27, which is just in time because the spacecraft will now start doing its first of its pointing maneuvers, and we'll be seeing wheel torque signals be coming through on our telemetry displays. As you see it coming through right now, you'll see that there's a wheel torque of 0.02 Newton meters being commanded to the wheels, and then the wheel torque will be given in the opposite direction again, and you'll see your wheel spinning up to -2000 RPM on the wheel speed displays. Maybe we can, Ben, you can even just make the NSS wheel a little bit better in view there. So what's good is we can see these wheel torque signals coming through, and it gives us, with the Acorn infrastructure, it gives us the ability to do a hardware in the loop simulation. As we can see now that it demonstrates the functionality of the wheel via this flat set environment that we have. And you can have it either at your own premises, or in this case, we have the wheel at the vendor development location, such as we have here at NewSpace Systems. And it's all connected, and you can test your components, whether it's local or whether it's a remote simulation environment. So if we have a look at the simulation, I think there's a second wheel torque command that will be shortly be coming up, as we see that on 3540, as it's just coming up there on your screen right now. And you can see your wheel speeds spinning up again then to above in the opposite direction, so about going up there at 500 and 1000 RPM. We've chosen this as a simulation just to demonstrate the changes in the wheel speeds and the torque command. So what's nice is this optical pattern, which we specifically just put for the demonstration today, which will obviously not be visible once the wheel is in space, but it gives us a visual reference of the commands being given, and it can show us that the commands aligns with the maneuvers that we're giving to the NewSpace simulated spacecraft, as we'll be see in the 3D visualizations. So we'll keep the wheel in view, and just feel free to observe it during mission as the vehicles continue. And I ask for Ben, we can ask for Ben just to tell us a little bit more about the next phase of the mission. So Ben, you can continue.
Thanks, Louis. So Dave, if we head back to the SDK visualization and we zoom in on that NewSpace Systems spacecraft, we should be able to see it beginning to, well, it's still in the process of conducting its surface point maneuver at Charles de Gaulle Airport is what we've picked for this spacecraft. So as you can see there on SDK, the spacecraft is conducting its slew maneuver. As I said earlier, we are taking a video of the ground here, so that spacecraft is going to turn to keep that field of view focused on its target. And what we'll have here is, after conducting the surface point, the spacecraft will return to a nadir pointing mode before subsequently pointing at Svalbard Satellite Station and conducting that payload and telemetry data downlink. If we return to the KISPE monitor screen, just point out a couple of things on the monitor that we can see, and I'll be able to show you some of the data that can be seen flying back from the simulation. So here we go. So as we can see here, a few things here indicating that maneuver is going on in the simulation. We have the flight software panel here is showing we're in a surface pointing mode, indicated by this 7, as you can see in the reference table below. But what we also have here is in this target parameters panel, it shows the line of sight vector of where the spacecraft is currently pointing. And as we're using the positive x-axis to point the space as the pointing axis of the spacecraft for this demonstration, you can see here that this vector is approximately a 100, showing the spacecraft is indeed pointed at its target. So I think if we'll leave this up for a little while, Dave is now going to talk a little bit about the significance of us having a physical reaction wheel connected hardware in the loop. Dave?
Yes, thank you, Ben. Yes, it's definitely important to have closed loop testing, as all of the people in this webinar are quite aware of. One of the things that is hard to do, though, is to find that time to do that early. So one of the nice things about what we're able to do here is we are able to do the closed loop NSS with the physical wheel in the loop. Acorn is sending flight software commands to the, Acorn flight software is sending commands to the reaction wheel as to what the speeds are that it would like based on the torques that it needs. And by doing that, it is sending that data to both the wheel and to the simulation model of the wheel we have. So that allows this physics to be stimulated so we can actually have the closed loop behavior of the rest of the vehicle. So really, even though we have a open loop piece of hardware inside there connected to this, we have the ability to feed that data through, and then the rest of the vehicle behaves as normal. So you're able to still do the things that you would like to do with that wheel, which is hard to do when you're doing this type of work. The other aspect of this is by doing this, we get a really good validation of our models. So we have captured data that's both what the wheel is actually sending out and then what we are responding with in the simulation. So we can do a very close analysis to make sure that we are indeed behaving as we would expect the actual wheel to do when we're doing our simulations. So with that, I think I've talked enough about that. I'll hand that back over to Louis. We can talk a little bit about more of the wheel and what we're seeing.
By looking at the simulation demonstration, we can observe the wheel speeds are in line with the physical patterns, and this just increases our confidence as we look at the wheel and the simulation and how it compares with the telemetry displays. So this increases our confidence that the wheel model and the wheel hardware are behaving similarly. So this is a real risk reduction and gives NSS customers using the Acorn the confidence that the control algorithms that they are developing for the space vehicle using our wheels will perform in the orbit as expected. Additionally, it's greatly reduces and minimizes the risk that upon final flight hardware integration, that there will be any issues with the interfacing, and more importantly, the performance of the spacecraft. So I think, Ben, you can tell us a little bit more about the next portion of the mission.
Thanks, Louis. Yeah, so I think looking at the simulation time, it'd be a good time to go over back to Dave's SDK, and we can zoom in on the KISPE spacecraft, which should, if I'm correct, be conducting its surface point at the Aral Sea in Kazakhstan. And again, we just picked this target as it's a good example of sort of environmental research you could conduct on a mission such as this. And in fact, it's just finished its pointing maneuver, so it's just returning to nadir pointing now, as you can see. We'll do that Svalbard ground station command in a second. Dave, if we head over to the Oakmont spacecraft quickly, we should be able to see it conducting its sun point maneuver. And as we're modeling a spacecraft here with fixed deployable panels, we need to point that spacecraft's solar panels at the sun to maximize that power generation by the solar arrays. So that's slowly spinning itself around to meet that sun vector. If we head back over, Dave, one more time to the KISS spacecraft, just to ensure we are in that nadir pointing mode, and I can make sure that we're ready to do that surface point. Here it comes. Perfect. So the spacecraft in its nadir pointing. And if we then go over to my monitor screen, we can show you how that command works. So as you can see now, we've got the telemetry back up. And actually what I'll do quickly before we do that is you just saw the Acorn spacecraft in the middle of its sun point maneuver. And we can see that here. It's indicated on the Acorn panel on the left in the green. We can see this battery state of charge indicator. And that's actually increasing, as we can see there. And we also have another panel down here displaying the charge rate of the battery. We have here, you can see the discharge rate is 0 because we're in a sunlit part of the orbit, and the solar panel is providing all the power we need to run the spacecraft at the moment. But as we've done this sun point maneuver to demonstrate that capability to you, you can see here this charge rate is positive and much higher than it has been at previous times in the simulation, especially compared to the NewSpace Systems spacecraft, which currently is not pointing at the sun at all. So you can see that difference there. So I think if we look at the simulation time, it'd be a good moment to conduct that surface point I was talking about earlier on. So what we can do here in this command console panel, you can see, is we can specify a location on the Earth for the KISPE spacecraft to point at. And what I'm doing here is I'm inputting the latitude, longitude, and altitude of the Svalbard ground station. And what we can do is we can send that command to the spacecraft, and it will execute that maneuver as we've commanded it to do so. So we've sent that command. I've just clicked that. And what we have is, if we look at the flight software, we can see it's gone back into a surface pointing mode as we're now pointing towards the ground station. These target parameters have readjusted as the spacecraft begins to move its pointing axis towards that ground station. If we head back to Dave's visualization, we should hopefully see that vehicle beginning to do its surface point very shortly. Brilliant. So as you can see, that the spacecraft is pointing at Svalbard ground station. It's slowly coming up to meet that vector pointed at the satellite station. I think we'll return to that a little later on and show you the SDK when the simulation's progressed a bit further. But Dave's going to talk a little bit now about the communications we've used here between our Acorns to make this all possible. Dave.
Thank you, Ben. Yes, so just want to talk to you a little bit about how this all comes together. One of the important parts of this is the ability for us to communicate across the globe with non-proprietary information channels. And we use message brokers to do that with. This particular demonstration, we're using the ActiveMQ messaging broker server. We could use MQTT. We have support for that. There's a couple others that we have support for. So we certainly are not tied to any one particular interface path. This does allow us to have disparate components and systems communicating together. So things anywhere from remote components like we're doing with Louis, where Ben is doing his mission design, even other hybrid architecture type things where we're seeing types of information that need to flow between systems. So our message broker piece is allowing us to do that. So that's a real potent thing for us to be able to do. It does give us lots of possible different integrations that we can use. And in particular, this case, we did do that with the wheel. And with that, I think we integrated that wheel pretty well. And so Louis is going to talk a little more about that.
Yeah, thanks, Dave. If I'm just looking here in our simulation time, it's 8:43 on the scenario. And I think there's a little bit of time that we can then talk about the wheel that we're using today and just focus on its characteristics and features. And I'll also just share a few thoughts on our production facilities. So if you have a look at this wheel on the PowerPoint slide, you will see it's a fairly small wheel. Its mass is roughly 1.5 kilograms, and its dimensions in millimeter is 102 by 102 by 104 millimeters. So it's about 10 by 10 by 10 centimeters. The model number specifically is derived from the maximum wheel momentum of 0.65 Newton meter seconds at maximum wheel torque of 20 millinewton meters, which it can provide. And it's also notable to have a look at the housing, because the housing is hermetically sealed. So the moving parts is therefore not exposed to the vacuum of space, which obviously contributes to the longer lifetimes that we're seeing with these wheels. So NewSpace Systems is quite proud that more than 64 of these units have been flying with no reported failures or single event upsets since 2014. And they are currently flying on other US constellation. So then obviously with no second chances to fix anything, if you have problems in space, the quality of one's manufacturing is extremely important, and that cannot be overemphasized. So ensuring that the reliability of the components and the subsystems is such that the system meets their lifetime reliability requirements. So and it's often these things which is not kept in mind by the prime contracting companies, and it's this aspect which frequently determines the success of a mission. So as such, here at NewSpace Systems, we have set up to be have a highly reliable type missions to be able to support, and also to support constellation programs. So as you can see, my colleagues, the technicians are all ESA accredited, where they're working in NewSpace facility, where we also have our quality processes ISO 9000 certified. So through our focus on the manufacturing, which is high quality, and our specialized experience with ADCS, the attitude, determination, and control system products, we've been able to support more than 50 prime contractors, of which 14 of them are national space agencies, and we assist them to achieve their mission success. And we soon believe that with all our components, we'll soon have Acorn interfaces, as we have a look at the ADCS components here, the sun sensors and the GPSs and the talker rods, and that soon we'll have Acorn interfaces and emulators so that you can use them in your own simulations and flatsats, or a globally collaborated flatsat demonstration as we have here today. So I think, Dave, you can tell us maybe a little bit more about the hardware integration, which makes this all possible.
Thank you, Louis. Yes, so we do interface with various different hardware components, especially those one-off type interfaces with our messaging broker and our bridges that we use to bridge the gap between TCP/IP to RS-422 to 1553 and SpaceWire. So we're able to adapt to whatever interface our customers have with their components that they need. So that's very helpful for them, as well as providing a really potent place to be able to test your interfaces and make sure that things are going the way you'd like. I think one last thing I'd like to do is just take one more look at the STK and see kind of what we're looking at here from each of the vehicles. And we'll check in on how they're doing with their downlinks. They should be getting ready to do that here momentarily, if not already. So there's the KISPE vehicle is doing its downlink. It looks like the NSS vehicle has already finished its downlink, and then the OAI vehicle is on its way to do its downlink. So we'll just jump over there real quick and take a look at that. And then what we can do next is we'll talk a little bit more about what this vehicle is doing as we're watching here. The Svalbard location is here, and we're getting close to doing that point to there. We're still doing a sun point maneuver. It's just been commanded to rotate around to start looking at the ground station. As you can see, it's starting to rotate there. So we'll watch this, but I think while we're doing that, I think I would like to go ahead and cover some of the last few things here we have to talk to you about. Again, this was a global effort, not just one person, not just one team, but multiple teams. So that was a pretty amazing feat. we're only demonstrating 3 of the 12 vehicles in this constellation, but there's no reason that we couldn't do more. We just only have so much time. So those are definitely a possibility. In the future, we may see something like that in our next demonstration. One of the key points that we're able to show you is that you can do your mission DRM really early in the process, which is really important. We do provide a basic flight software capability, so you can do those things. One other thing is Ben mentioned is we are flexible. We have that configurability that allows you to modify your parameters to make wheels and GPS systems and power subsystems and components that you'd like, just depending on your mission needs. So you have that opportunity as well. And then also we give you the opportunity to do early hardware integration, as we've demonstrated here with Louis and NSS, is that the earlier you can do that, the better off you are, at least when you're talking about physical interfaces and performance of physical components. So with that kind of capability, we really do help reduce mission risk and schedule costs and all the good things that we need to do to make vehicles and space more cost effective, as we're all trying to do these days. And the added bonus of being able to work globally. So we spent about a month together, I think the 3 of us have, and we've gotten to know each other pretty well. So we've had a lot of fun together, and we've learned a lot about each other's culture. So that's always a good thing too. One last thing to mention about this is that our messaging subsystem is really the critical piece to this. The ability to use that really allows us to do hybrid architectures, which is really the wave of the future now. Is like you see lots of that about what we're doing here with small satellite space. So with that, I'd like to just close out by thanking the team. The team's been spectacular. We've had a lot of support staff from each of our IT departments from each company here. The marketing team, they're the ones that keep us on track and making sure that we say the right things and we do have a good product to show you at the end here. And of course, the engineering team, KISPE has really, learned a lot about how brilliant other engineers are across the world, and it's kind of a little eye-opening to see how incredibly talented these people are across the world. So I feel like that our future space is in good hands with these gentlemen. Well, I think with that, I think we are finished up here. I'll hand it back over to Danielle, and we'll look in to see whatever questions we have that popped up through the process here. Danielle?
Thank you, and thank you all of you. That was an awesome demonstration. We did have some questions come in from the audience, so I would like to invite the executives to join us with their webcams if they would like to weigh in. And if we run out of time here, just know that your questions will be answered. We will contact you if we do not get to it today. And with that, our first question will be, I believe, for OAI. Virtually all satellites now contain a GNSS unit integrated into the satellite bus. How is this being tested in the Acorn?
Dave, can I just jump in real quick?
Sure, go ahead.
Yeah, so the interesting part is we've actually integrated a NSS GPS receiver into the Acorns here in Littleton, Colorado. We also tie in, we can do static testing via re-radiator on the rooftop of live GPS signals. And then we also tie into ground support equipment, either Spirent, the old Nortel test sets for GPS constellations. But we do have fully tested interfaces for the GPS that's NSS has provided.
Great, and we have another question from Matthew. Is time synchronization between the nodes required, especially with this demo showing actuation over WAN? It looks like there would be much higher latency than on the spacecraft between commands and the actual device's response. How is this managed?
So that's a good question. Yes, we do have to deal with delays and lags of that nature, but we use onboard synchronization to keep that alignment as it should be. We also have the servers that are running locally, so despite the data flowing from far away, most of the local data is located within the same network as the actual unit under test. So really it's just the commanding piece and the telemetry piece that's coming from far away. The local units have their own servers running with them, so they're synchronized to that.
Great.
That's a good question. Thank you for the question. It's good.
And then we have a question from Pierre. Thank you for this presentation. Myself coming from a defense background, maintenance I have found is an important part to consider during design. Obviously, in the space environment, accessibility gets a new dimension in comparison. To what extent can maintenance be performed on a system in operation?
So I think, Stan, do you have any thoughts on that, or should we just table that one? That sounds a little complex and might take a little more time than we have today to answer.
Yeah, I can give just a brief overview. I think many of the new systems are going to software definable and reprogrammable systems. And so I think from a maintenance perspective, being able to do the debugs early on and being able to use Acorn interfaces with some of the software defined interfaces of the hardware that's coming online is going to help with some of that maintenance. Obviously, once you're launched, hardware is hardware. So we're looking to Louis and James to do good hardware practices, and I know they've got those well in hand. But from a software update, software patch compatibility, I think that's where some of the new systems are going. James, did you want to comment on the hardware test?
Well, I was going to add, at the end of this process, you've got an Acorn running, which has got a full ground to satellite simulation. So you can still send it commands. So if your spacecraft's not behaving, you can compare the behavior in orbit with your simulation on the ground, and that will help you try and work out what's happening remotely.
Very good point, James.
Great. Our next question is from Martin. How involved are the commands you are sending to the simulator as far as if from the ground? Example, are you sending attitude updates to take an image, or are you sending one command to point and click?
For that, yes, we are sending one command. The onboard flight software has given instruction as to where to point, and it does all the other attitude calculations that need to be done, including controlling the actuators and using its sensors to see if that it's actually doing what it's supposed to be doing, and then correcting for it if it finds errors. So the onboard flight software is actually doing that. For us on the ground, LEO vehicles are difficult to really command live just because of line of sight type situations. You really can't talk to them very frequently. So almost every LEO spacecraft will have some type of onboard command management system to help with those kinds of things. That's what we're doing here in this demo.
Great. And I think we have time for just a couple more. One question from one of our attendees says, as a fellow ADCS and systems team lead, I appreciate the demonstration. How would you say one should approach the design of their flat sat?
So I don't know, Stan, that sounds like a question you might like to answer.
I'll give it a go, and then John, probably you should add in a little bit to it. But I'm a GN&C guy myself. Started out in flight controls. The nice thing about Acorn and being able to get the early simulations going allows you to do a lot of testing with your ADCS subsystem or GN&C subsystem algorithms, as well as doing the hardware in the loop. So as a console operator for a long time, more testing, more time on the system, and really wringing out the algorithm description documents and the test scripts and the task lists becomes very, very important. But John, maybe a little bit about KISPE mission operations rigor that goes into those designs.
Yeah, so you're right, Stan. I mean, the bit that we like about it is the fact that we can very quickly come up with a design reference mission. So we can do our initial AOCS design, we can do our initial sensor actuator selection. We can embody those into the implementation within the Acorn for the design reference mission. And then we can start to simulate that mission. And so as we start to simulate and test out that configuration, at that point we can then start to look at whether or not we need to swap the sensors and actuators out for different types. So it gives us that flexibility. So what it allows us to really do is bridge between the sort of paper design, as it were, and the physical implementation, which I think is quite powerful. So where we see value is in maybe being able to compress the stage between that initial concept design and the realization of the system. And so some of the models that we're getting now, some of the subsystems and equipments are are pretty accurate in comparison with the real hardware. So it helps de-risk some of the missions, which is good.
Great, and we have one more question. I believe this will be a good one for all three execs to weigh in on. Dr. Scalise yesterday during his keynote mentioned hybrid architectures. So maybe just some comments on how this demonstration can inform the future of hybrid architectures.
James, you want to go first?
No, I don't want to go first. This is system level stuff, so
yeah, I guess the good thing, I mean, the demonstration today was as Ben said, we demonstrated, or we showed 3 satellites of a constellation of 12 spacecraft, and in this instance, all 3 spacecraft or 12 spacecraft are identical. There's nothing stopping us from modeling any type of constellation or system, for that matter, where each of the individual nodes may be different. And so we have the flexibility to do that. One of the things I'm excited about that Stan and the team are working on at the moment is the virtual model instances. So that will enable us to have multiple instances of the Acorn, each of which will be a specific satellite configuration. And then that should allow us to start looking at distributed constellations and system of systems. So I think that power is really good. It enables us to say, test out a full system without having to have racks and racks of equipment, which is definitely a step in the right direction. At the same time, though, you know, with the version that James has got, we can still go ahead and do hardware and the loop type testing as well. So I think it opens itself up. You know, we're not locked to a particular spacecraft configuration. Each of the spacecraft in our simulation can be different.
Yeah, I totally agree, John, and I also think with where the industry is going with machine-to-machine data sharing and the electronic ICDs for those things, like the databases that are available through NASA and ESA with the parts databases that NSS is a part of, those are going to become much more important. Being able to bridge those electronic ICDs, bring those pub sub services into or out of those systems very rapidly is what's going to, like you said, accelerate the timelines, but not just accelerate the timelines, but still put the rigor into the testing that continues to provide increased mission assurance. And so I think NewSpace, you know, the 1 years are going to 3s and 5 years, and much more emphasis is now they got to get up and work and infant mortality and other things. So having that capability of merging, you know, the built-in test emulation and the mission assurance aspects while still compressing the timelines, that's a win-win for the end customers.
Great. Well, if anyone has any closing remarks, now would be a great time to do that. Small sat events start at 10 a.m. Mountain Time. So we want to give everyone enough time to get there. But if anyone has any other comments, this would be the time.
Yeah, I'd just like to add kudos to the team. You know, James and John and I get to stand up here and field some questions, but the hard work is Ben and Dave and Louis and all the folks that have provided it. So just hats off to the team. This is fantastic.
Yeah, it's brilliant. Cheers, everybody. It's been excellent.
Awesome. Thank you all for attending. Goodbye.
All right, take care.